Hi. So to get everyone started today, I have these two problems for you to think about for a minute or two. Feel free to pause the video, come up with an answer for both of these based on what's on the slide. But I'm going to go through them now. For the first solution, these are both based off of chromic acid, as it says on the top, H2CrO4. This first one is going to be, keep in mind, the sodium dissolves into solution. So what we're left with is HCrO4 minus, and then for the second solution, CrO4 2 minus. For the first solution, this is the intermediate of a diprotic acid. So let's just jump right in. The H plus concentration should be equal to K1 K2F plus K1 Kw over K1 plus F. That's the square root of. For this K1, keep in mind when we have this pK1 being negative, that actually means that the K1 is equal to 10 to the positive 0.98. This chromic acid is fairly strong for the first deprotonation. But plugging in all the numbers there, the first answer should give you H plus equal to 1.269 times 10 to the minus fourth molar. And that yields a pH value of 3.90. And that should make sense for your intermediate form. Given that this is a relatively strong acid, it's still low pH, but not as low as it could be. And starting for the second one, starting with the fully basic form, let me switch my colors really quickly. Starting with the fully basic form, the guiding reaction here is going to be Kb1 is equal to hydroxide times the intermediate form over CrO4, the fully deprotonated form, or x squared over f minus x is equal to, and because pKb1 is related to pK2, they should add up to 14. So pKb1 is equal to 14 minus 6.49 is equal to 7.51. This should be equal to 10 to the negative 7.51. Throwing this into your graphing calculator, this should give you a value of x, this being the hydroxide concentration, of 3.929 times 10 to the negative fifth molar, and that yields a pH value of 9.59, which does make sense considering that it's a base. So for today, we're going to actually look at an extension of our diprotic systems, a triprotic system. The biggest difference between them is that for your diprotic system, our fully protonated species is H2A, A being the just whatever anion is present or whatever rest of the molecule is present. And that, as we deprotonate, would create an HA minus species, which could then further deprotonate to give an A2 minus species. For a triprotic system, there are three protons that can be pulled off of this molecule, which would then yield first intermediate of H2A, a second intermediate of HA2 minus, and a third, not a third intermediate, a final product, the fully basic A3 minus. So this means instead of 2 K values, you should actually have 3 K values, and the reactions that correspond to them are shown here. Of particular note here is that K1 is related to actually Kb3. If we look, here we've got our H3A and our HA2 minus species, and those two species actually show up in the third base. So the way to think about this is to say the first deprotonation corresponds to the last protonation. So when multiplying them to figure out the values, Ka1 times Kb3 equals Kw. You can also say that Ka2 times Kb2 equals Kw, and Ka3, or K3, times Kb1 equals Kw. And those relationships will carry through if we get into 4 or 5 or more protons. So the first deprotonation corresponds to the last protonation. So I just wanted to step in really quick to each example of the species of A being a triprotic conjugate base with the reaction shown. I'm going to really rush through the systematic treatment part and just kind of jump straight to the approximations to allow us to quickly come up with some formulas. If we're starting with just the H3A species here, Obviously, these values, since these are weak acids, these values aren't terribly large. Yeah, K1 is the largest of the three Ks, but still not super large. So for our approximations, we're going to say that not much H2A is formed, but furthermore, even less HA2 minus is formed, and then even less A3 minus is formed. So this basically collapses down into a monoprotic system. And so in that monoprotic system, we learn that Ka, in this case K1, is equal to H plus times H2A minus over H3A. Or if you plug in x equals H plus and go through the systematic treatment, you get x squared over F minus x. For the H2A being your starting material, the equilibria that are going to take place, well, looking at the reactions that have H2A as a reactant, we're going to be looking at Kb3 and Ka2. Keeping in mind that neither one of these is a very large number, most of your H2A is going to stay as H2A. And so at equilibrium, your H2A minus concentration is going to be roughly equal to F. Instead of looking at the Kb3, I am going to come up here and instead look at the K1, just so that we're using all acids. But this should look very familiar to our intermediate form of a diprotic acid, and that's exactly how this works here. So after you step through the systematic treatment, what you end up with is H plus is equal to the square root of K1, K2F plus K1, KW, all divided by K1 plus F. And then you just plug into your calculator. For the intermediate HA2 minus, looking at our equations, again, if we circle all the times that HA2 minus shows up as a reactant, we again are finding two reactions, Ka3 and Kb2. So again, we've got like two things to consider, but both are small, so neither one really contributes a lot to the pH. So this sounds a lot like the previous case, and actually if we think about it, if I'm going to circle up here and again only look at the acid reactions with HA2 minus, we're used K1 and K2 in our first intermediate. So looking at our second intermediate, it looks pretty similar to the last case where the only difference is we're using K2 and K3. And so the way your book goes through this, and I support this, is to look at the Ka expressions that surround your intermediate and use those to guide the formula. But if you do step through the systematic treatment, I don't really want to do that right now. I think that would take a while, and it's not really the purpose of this video. Maybe I'll record another one later. We can just kind of jump to the end here, where the H plus, it's going to be a very similar expression, except instead of K1 and K2, we're just going to put K2 and K3 in their place. So it's K2, K3, F plus K2, KW, all divided by K2 plus F. Again, it's instead of 1 and 2, it's 2 and 3. If this was a tetraprotic system and you had a third intermediate, that would be K3, K4F, and you go so on and so forth for each of your intermediates, which is kind of nice. That means after you look at a couple of these, you can extend out to as many as you need to. And then finally, looking at A3 minus, well, the only place that A3 minus shows up as a reactant is here is KB1. And similar to our first example, KB1 not going to be terribly large, KB2 and KB3 even smaller. So we're going to kind of say that not much of this gets made and then even less of this gets made. So that what we're left with is a monoprotic base, or a mono base. So instead of K1, we're going to use KB1, which is equal to KW over K3. And that's going to equal, it'll be hydroxide times the HA2 minus, over the A3 minus concentration. And then if you substitute an X for the hydroxide ion concentration, what you end up with is X squared over F minus X equals KB1. And then you just solve with your calculator. So looking at these four examples of how to treat a triprotic base, I thought it would be a good idea to just go through the process of calculating the pH for one triprotic system at each starting material of the each possible starting material. So what we have here is the amino acid histidine, which, similar to what we saw this with leucine, there's obviously the amine group and the acid group, but in this case the side chain actually has some acid-base properties of its own. But we can see that this K1 here corresponds to losing the acid H+. K3 here corresponds to losing the amine part. And then, so in this case, PK2 with this PK2 of 6 corresponds from going from this NH+ to just an N. So that this amino acid should be fairly similar to what you've seen in other amino acids, where K1, the acid K, is close to 10 to the minus second, and the amine K is close to 10 to the minus ninth. So stepping into it, the first example of H3 his Cl2, this would dissociate in water to make H3 his 2+, which for us is going to be equivalent to H3A. Yeah, the charge balance would look a little different, and we could go through that. If you want to go through that on your own, I support doing so. Just don't forget that the chloride is there as an ion and for your mass balances, and the chloride ion concentration in the solution would be 0.2 molar instead of the 0.1 you might be expecting. But applying our approximations here and our formulas for this form, this fully acid form here, what we should simplify to is K1 is equal to H+ times H2A minus over H3A. And then when we start plugging in some numbers, we should get 10 to the negative 1.6 equals x squared over 0.1 minus x. And when you throw that at your calculator, what you should get is x is being the hydronium ion concentration is equal to 0.0391 molar, and that should yield a pH value of 1.41. Looking at the second form, the first intermediate, this would be in water, H2 his plus, which would be like saying H2A minus. Here the neutral species is the second intermediate, but that doesn't really, again, impact our math very much. But when you're looking at this substance here, we're going to look at the K's that surround it to come up with our equilibrium, or for our H plus expression. Using our intermediate form formula, K1 K2F plus K1 KW over K1 plus F. And then if I'm going to take the step of plugging in just so we can be 100% on the same page with how we're doing our calculations. And when you plug all of this in and you put it in your calculator, what you should get is 1.47 times 10 to the minus fourth molar, which would give you a pH value of 3.83. This should make sense because this is less acidic than the last form, and since you're starting with one fewer H and you're kind of starting at K2 as your first deprotonation, that should logically follow. Looking at this H his here, that's corresponding to HA2 minus in terms of our previous formulas. So that's this species here. And so we'll be looking at the two K's surrounding being K2 and K3. So same deal as before. Here we're going to do K2 K3F plus K2 KW, all divided by K2 plus F. Plugging in actual values here, we should have 10 to the negative 5.97, 10 to the negative 9.28, 0.1 plus 10 to the negative 5.97, 10 to the negative 14th, all over 10 to the negative 5.97 plus 0.1. And when you throw that at your calculator, what you should come out with is 2.37 times 10 to the negative 8th molar, and that the pH here is equal to 7.62. So again, we're following our pattern. Each successive, starting with your starting material being each successive intermediate or more basic forms, you're getting a higher and higher pH, which again logically follows. And then finally, looking at this, when this dissolves into water, the sodium's going to fall off. You can again go through the systematic treatment. Just keep in mind that the sodium is there for the mass balance, but it's not really included in anything else. But this does correspond to our A3 minus form of histidine, which is this bottom one here, which means this is the fully basic form. So we're going to apply the monobasic approximation. KB1 equals x squared over f minus x, or in this case, since pK3 is 9.28, KB1 is 10 to the negative 4.72 equal to x squared over 0.1 minus x. And don't forget at this point that x is equal to the hydroxide ion concentration, which should give you 0.00137 molar, and your pH value being 11.14. So hope this all kind of made sense to you. If it didn't, you're welcome to go back and watch it again, watch through the steps I'm taking. But for your homework for tomorrow, I want you to look at this this second situation, very similar situation to what we just went through. Hypothetical acid H3A weak with the 3K shown. I want you to do a full workup. So in each case I showed you how to find the pH. From there and the approximations that you made to get to the pH, you should be able to use the K expressions to find each of your substance concentrations. I'll put something up so that you guys will have a form to fill in or a worksheet to fill in to make this easier. But yeah, good luck with this, and if you have any questions, you can post them below. Thanks.